Video Lecture 16C, The Acid-Base Nature of Salts. As you can recall, salts are compounds that are formed in an acid-base neutralization reaction. The name of that type of reaction implies that the salt solution that results will be neutral, that is, neither acidic nor basic. This only occurs when reacting a strong acid with a strong base. However, if a weak acid or base is involved in the reaction, the salt that is made may alter the pH of the solution. To determine whether or not a salt is acidic or basic, or even neutral, we have to look at the acid-base properties of our constituent ions. Ions can make a solution acidic or basic by reacting with the water. This reaction is called a hydrolysis reaction. It is very similar to an acid or base ionization reaction, except that one of the reactants is an ion. For example, the ammonium ion is considered to be a weak acid. When it reacts with water, it will transfer a proton to the water to form the hydronium ion, H3O+. It will also form the conjugate base of ammonium, which is the ammonia molecule. This reaction is a good example of a hydrolysis reaction. We will need to know how to write these types of reactions, especially when we perform calculations that involve titrations. To classify a salt as acidic or basic, we have to look at each of the ions that make up the salt. We first take a look at the types of cations that can be involved. Cations that are counterions of strong bases tend to be neutral. That is, they do not appreciably affect the pH of the solution. Counterions of strong bases are the metal cations that are associated with the hydroxide ion for the formula of a strong base. These ions include lithium, sodium, potassium, calcium, strontium, and barium. The second category of cations are cations that are conjugate acids of weak bases. These cations tend to make the solution weakly acidic. For example, the ammonium cation is a conjugate acid of the weak base ammonia. Therefore, the ammonium ion is considered to be weakly acidic. The methylammonium ion, a derivative of ammonium, is also considered to be weakly acidic. Its conjugate base, methylamine, is also considered to be a weak base. The third category of cations are cations that are very small but have a high positive charge. These are usually transition metals or late main group metals that have a charge of +3 or higher. These cations interact with the water molecules in solution to make the hydrogens more acidic. Therefore, these cations in solution are weakly acidic. Some examples of small highly charged metal cations are the aluminum 3+ and iron 3+ ions. Now we can take a look at the basicity of anions in solution. Anions that are conjugate bases of strong acids tend to not affect the pH of the solution. Therefore, they are neutral anions. We could take a look at the conjugate bases of all of the six weak acids that we have encountered in class: chloride, bromide, iodide, nitrate, sulfate, and perchlorate. The second category of anions are anions that are conjugate bases of weak acids. These anions tend to be weakly basic. For example, the fluoride ion is the conjugate base of the acid hydrofluoric acid. Since hydrofluoric acid is a weak acid, then fluoride is considered to be a weak base. The same thing goes with the acetate ion. Since acetic acid, its conjugate acid, is a weak acid, then the acetate ion is expected to be a weak base. Now it's time to put everything together. First of all, if the cation in the salt is neutral and the anion in the salt is neutral, then the salt is expected to make a solution neutral when dissolved in it. Sodium chloride is an example of a neutral salt. Sodium is the counter ion of a strong base, and the chloride ion is a conjugate base of a strong acid. Therefore, sodium chloride is expected to be neutral. If the cation tends to be acidic and the anion is neutral, then the salt solution will be considered acidic. For example, ammonium chloride consists of the ammonium ion and the chloride ion. The chloride ion is the conjugate base of a strong acid and is therefore neutral. But the ammonium ion is the conjugate acid of a weak base and is considered therefore to be weakly acidic. Therefore, ammonium chloride is considered to be an acidic salt. And when it dissolves in water, the ammonium ion will undergo hydrolysis to form H3O+. If the cation in the salt is neutral and the anion is basic, then the entire salt will be considered basic. For example, sodium hypochlorite, one of the major components in bleach, is considered to be a basic salt. This is because the hypochlorite ion, shown in red, is the conjugate base of a weak acid, the hypochlorous acid. This makes hypochlorite a weakly basic. The sodium ion is the counter ion of a strong base, sodium hydroxide, and is therefore considered to be neutral. This makes sodium hypochlorite a weakly basic salt. What happens if your cation is acidic and your anion is basic? Then we need to start to look at numbers to quantitatively determine whether or not the salt will be acidic or basic. The pH of the solution will depend on the relative strengths of the acid and base. This means that we need to compare the Ka for the weakly acidic cation and to the Kb for the weakly basic anion. If Ka is larger than Kb, then the solution will be considered acidic. If the opposite is true, Kb is larger than Ka, then the solution will be considered to be basic. If Ka and Kb are about equal, then the salt solution will actually be pretty neutral. Here's an example. Suppose we look at ammonium fluoride. Is it going to be acidic, basic, or neutral? Well, let's take a look at the ions that make it up. Ammonium fluoride breaks down into the ammonium ion and the fluoride ion. The ammonium ion, as we saw before, is an acidic ion. The fluoride ion, being the conjugate base of the weak acid hydrofluoric acid, will be considered weakly basic. We can look up the Ka and Kb for the ammonium ion and the fluoride ion respectively. For ammonium, the Ka is 5.6 times 10 to the minus 11, and for fluoride, the Kb is 1.5 times 10 to the minus 11. Comparing these two numbers, the Ka for ammonium is slightly bigger. This means that The ammonium fluoride ion is an acidic salt. We could calculate the pH of the salt, but that's beyond the scope of this course.